What the heck?
Tagon.
I want to do one more neat thing with a result that we've derived previously, which was this. We derived the very, very nice fact that now we can sort of say complex numbers because we know the restrictions, right? The zth harmonic number is equal to the sum from k equals 1 to infinity of z divided by k times z plus k, right? And we discovered that the only terms in this that you can't plug in for z are actually just the negative integers. And you can actually see that that's the case from the original definition of the harmonic numbers, right? If the original definition of the harmonic numbers using a positive integer n is the sum from k equals 1 to n of 1 over k, and we have pretty good definitions, right? What this tells us is that we can write h sub n as the previous one, h sub n minus 1, plus the next reciprocal, right? You see what I'm saying? This is sort of the original recursive definition for the harmonic numbers. But now that means we can solve for the previous harmonic number simply by subtracting 1 over n over. So we have that the n minus first harmonic number is equal to the next one, the nth harmonic number, minus 1 over n, which means we can sort of derive from pretty first principle arithmetic what the zeroth harmonic number is, because we've sort of not really justified that. It sort of just fell out of the math as being 0. But notice that if we plug in 1 for n, because we know h sub 1, so this is an example, we know that h sub 1 is 1 because you're adding the first reciprocal of the natural numbers, right? So it's 1. So that tells us that the 0th harmonic number, or the 1 minus 1, right? 1 minus first harmonic number, I'm just plugging in 1 for n, is going to be equal to the first harmonic number, which is 1, minus that reciprocal 1 over 1. And of course, what's 1 minus 1? It's 0. So that's sort of the first justification as to why the 0th harmonic number is 0. But then as soon as you go one more step, this breaks down exactly in the same way if you tried to define the factorial for negative numbers. Because what do we have to do to get from the 0th harmonic number to the negative first harmonic number? Well, we have to do h sub 0 minus 1 over 0. And this would be the negative first harmonic number. But immediately, we realize that we can't do that because we're dividing by 0. And as soon as the negative first harmonic number is undefined, therefore this one doesn't have a value, trying to find the negative second harmonic number, which would just be the negative first harmonic number minus 1 over negative 1, right? This would be like adding 1, but the point is, even though this is well defined, this isn't, because the only way to define this is in terms of subtracting the reciprocal of 0, which simply doesn't exist. And so because of this cascade, because of this one fact right here, where the negative first harmonic number is not well defined, then that sends a cascade down the negative integers that shows that none of them are well defined. So that's just the sort of arithmetic justification, or I guess algebraic justification for why none of the negative integers work for the harmonic numbers, which is why you see that here, right? We can't plug in negative integers for z because then we would be dividing one of the terms in this infinite series by 0, which would make it undefined. So you're sort of getting the justification for that from different directions, but they all agree with one another, and that's sort of the important part. That wasn't the only thing I wanted to take a look at for this neat series right here. What I wanted to do was actually rewrite it in the original form that we saw it as, which was as two separate fractions being subtracted from one another. Because what that allows us to do is write it as 1 over k minus 1 over z plus k. Right, that's what we had. You can confirm that if you distribute those things in and then add them together, you end up with that fraction right there. But what happens when you have a difference of things that are sort of in the same form, but with different inputs? Well, you can write it as a definite integral, right? Because you can think of k and z plus k as the inputs of whatever this integral is. So think about it. This is identical to saying we have the sum from k equals 1 to infinity of the function 1 over x evaluated at k and z plus k. Right? Exactly like you would write the answer to an antiderivative. But we know what the antiderivative of 1 over x is. It's negative 1 over x squared, right? So we can actually write this as the sum from k equals 1 to infinity of the integral from z plus k to k of negative 1 over x squared dx. Right? I hope that's clear what I just did there. Now, I want to be able to put the sum inside of this integral, but I can't do that until the indices of the integral no longer depend on k. So what I need to do, first of all, use this negative to flip indices. So I'm going to just distribute the negative into the integral, so we get that it now goes from k to z plus k, instead of from z plus k to k. I know there's no implication that z is necessarily more than k, because, again, z could be a complex number. It just looks nicer that way because there's more terms, and now there's not an extra negative sign under the integral, which is just nice cosmetically. But what we can do to make sure that the integral no longer depends on k, so that we can put the sum inside the integral, is to simply increase the function by k. So we're going to plug in x plus k for x, which is going to cause both of the indices to go down by k, just like we would do with a sum in case we wanted to shift the indices. So this is the same thing as the sum from k equals 1 to infinity of the integral from 0 to z, because all I'm doing is removing k from these by adding k to the 1 over x, and we get the integral, the integrand is now x plus k, 1 over x plus k squared dx. I hope that's clear what I did. I just added k to the function directly onto the input of the function, which decreases the indices by k, which means now the indices no longer depend on k. So I can put the sum inside of the integral quite nicely, and I get that this is equal to the integral from 0 to z of the sum from k equals 1 to infinity of 1 over x plus k all squared dx. Now, this is where it gets interesting, and this was brought up in comments in the last couple videos. How might this be related to the Riemann zeta function? Well, if you take a look, it looks like we've got a pretty close representation of the Riemann zeta function here. It's almost like it's zeta of 2, right? We've got a 2 in the numerator there, but instead of just summing over k's, we've got this extra term x. So what we need to do is consult something, a more generalized version of the Riemann zeta function called the Hurwitz zeta function, which is, I'll write it over here, it's Hurwitz zeta function, which is simply, I'm going to just delineate this, which is simply a sort of generalization of the zeta function. So it's zeta of s comma q, that was almost a g, s comma q, where this is equal to the sum from k equals 1 to infinity of 1 divided by k plus q to the s. So it's sort of adding another parameter to the zeta function, and it behaves quite similarly to the zeta function. But what we can do is simply replace q and s with the things that we're actually adding in this function, right? So the zeta function would just be without this extra parameter q, and if it were 0, then we would just get the zeta function. I think it's clear to see that if we had, so zeta of s comma 0, then this would just be equal to the Riemann zeta function, right? Because then this extra parameter is gone, and so it would just be 1 over k to the s, which is exactly what the summand of the definition of the Riemann zeta function is just 1 over k to the s, and then you pick what s is. So for q equals 0, it's the regular Riemann zeta function. But for other values, it's this generalized Hurwitz zeta function. So we can actually replace that and write it like this. So we have the integral from 0 to z of this Hurwitz zeta function, which is going to be zeta of 2 comma x. K is the running index, just like in the original definition, so x is the q in this case, and 2 is s. I hope that's clear. So this is the integral from 0 to z of the Hurwitz zeta function of 2 comma x dx. So I can probably erase this definition now. My point of sharing this is that although this seems a little exotic with regards to the Riemann zeta function, this is very, very intimately related to the zeta function and the study of zeta functions and prime numbers and so on. So this is not an arbitrary thing to try and put into an integral. This is sort of the first piece of evidence that there is a connection between the harmonic numbers and the zeta function without sort of assuming anything else, right? Just from pure exploration of the harmonic numbers, we come upon some form of the zeta function. And so this should pique your interest, because we're eventually going to prove that integral that I wanted to show you over the harmonic numbers, and it's going to have a lot to do with things that end up being related to the zeta function and the gamma function as well. So I hope that everyone's excited for that. This is the other thing I wanted to show you in this video. I have many, many more things to show you about this series because it's just such a beautiful piece of mathematics. So I hope that you enjoyed these little factoids that I've shown you in this video. and stay tuned for more, because there's much more to come. And I just wanted to give a special thanks to all the people that are saying such wonderful comments in the videos. I really appreciate the members of my audience that participate in conversation and ask really, really cool questions. I really, really appreciate it. Thank you so much to the people that are subscribed and that watch and that ask such cool questions. I'm always happy to answer questions. No questions about the math are silly, because if you simply have a misunderstanding, it can always be clarified. There might be something confusing to you, and there's nothing wrong with that. Oh, I wanted to share something a little extra. I wanted to introduce one little quick concept called the harmonic mean. So it's the same idea almost as an arithmetic mean, except it's slightly different, right? An arithmetic mean is the sum of like some n terms, right? x1 plus x2 plus ... plus all the way up to xn. And then because there are n terms, you simply divide that whole sum by n, and that's the arithmetic mean, or average of the n terms. Similarly, the geometric mean would be like if you took the product of all of those terms, x1 times x2 times ... all the way up to xn, and then raise that whole product to the 1 over n power. It's sort of like the geometric version of that, right? It's a product to the 1 over n power as opposed to a sum and divided by n. The harmonic mean is the reciprocal of the average of the reciprocals of numbers. So this is the harmonic mean of those x terms. So it's n divided by 1 over x1 plus 1 over x2 plus ... all the way up to 1 over xn. This would be the harmonic mean of a set of numbers. And I just wanted to show you that for the harmonic numbers, which are the sum of the first n reciprocals, right? This is 1 over 1 plus 1 over 2 plus ... plus 1 over n, right? Each term in this series is the harmonic mean of the two next to it. So what I'm saying is if I have 1 over k, and then 1 over k plus 1, and then 1 over k minus 1 on the other side, if I take the harmonic mean of these two terms, I get the term in the middle, which is quite easy to see. There are two terms, so the numerator of that harmonic mean is going to be 2, and we're dividing by the reciprocals of the sum of the reciprocals of these two things. So it's going to be 1 over k minus 1, which is just k minus 1, plus 1 over k plus 1, which is just k plus 1. So we're adding k plus 1, and look at that, the 1's cancel, and we get 2k in the denominator, so we get 2 over 2k, which is of course equal to 1 over k, which is the term that I said you would get in the middle. So every term in the series of the reciprocals of integers is the harmonic mean of the two surrounding terms, and that works for all of the k values, which is quite a neat little fact. One other thing I wanted to mention just before my camera runs out of time is... Actually, I think that's it. I think that was all the facts I wanted to share for these videos. So stay tuned for more fantastic harmonic series stuff. I'll have another video coming out soon. Again, thank you so much to all the people that are watching these videos. I really appreciate it. Quick little thing, this channel has an Instagram, so it is at whatthehectagon, of course, and it has a Twitter, and it is of course naturally, also at whatthehectagon, and my email is the incorrectly spelled whatthehectagon, why spell check before you make the email, right, that you can't then change, at gmail.com. Now, all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down. That's the stuff. Thank you for watching, and bye-bye.